You can also do something else. For example, you can solve the nice electrodynamics problems. You can say put epsilon 1, epsilon 2, and epsilon 3 here. And then you will find that if you look at two charges that interact at a distance that is shorter than this d here, then it is basically epsilon 1 plus epsilon 2 half is the effective dielectric constant. If you have two charges that are separated by a distance that is larger than this d here, then they will interact by a dielectric constant that's epsilon 1 plus epsilon 3 halves. What is important here is that if you can screen the Coulomb interaction in the system, for example, if this here was a metal, easily at large distances. But you cannot easily screen the Coulomb interaction by interband excitations in this two-dimensional plane. That's not really possible. There were claims that this could be done, and it's just not possible in the sense of straightforward electrodynamics. Yes?
You're assuming here the dielectric constant is linear and isotropic.
Linear in what?
Are you assuming it's a linear dielectric constant? As just like
I don't consider nonlinear optics in this simple discussion here, no.
And how about isotropic? Do you know, is there a way to gauge the validity of, like, is it linear?
Oh, what you can do is you can introduce here an anisotropic tensor. You can solve the same problem again, and then you find that the traces of the dielectric constants proper weight are. I mean, you can always find an effective dielectric constant in the plane easily. But it's just getting a little bit more tedious. So I solved this problem here just for fun, and you will find then that, of course, in the distance, you can have a distance-dependent Coulomb interaction by geometric setups. But for example, even for isotropic systems, you could do this more complicated if you wish to. I don't think. But I'm not scared of that problem, or I don't expect anything interesting to come out of it.
The spatial wave functions of the electrons kind of penetrate into these epsilon 1 and epsilon 2s, right?
Not in this logic here, not in this simple-minded problem. Here, this is the result of a calculation where you say at the two-dimensional surface density, the electrons do not penetrate and therefore modify the electric constant of those media. So I'm looking at distances larger than, say, an atomic distance.
No, okay, but what I'm saying, you need to integrate out this dimension, right?
I need to integrate out the electric field in that dimension, not the electron wave function. The problem we have here, that's what I was trying to stress, is we have a two-dimensional electronic system, but the electromagnetic field lives in 3 dimensions. And therefore you will have to integrate out the QZ component of the vector potential if you wish so, right? Because the field lines truly go into this 3-dimensional space. And that gives rise to, on the one hand, the dielectric constant will also give rise to something else, as we will see as we read on. But it will really only, see, the interesting thing is you can tune the Coulomb interaction in the system by modifying the substrate. That's the message.
It also gives rise to the fact that Coulomb potential is not really exponential, but there are some flat parts.
Right. So you can, they're interesting, I mean,
almost flat.
But those, well, there are two questions here. One is, what is the right Hamiltonian, and what is the renormalized Coulomb interaction of that system, which is, I think,
but different dependencies.
Absolutely.
They come from either.
Yeah. Good. So I became aware of this problem when I visited Florida State, and talked to Oscar Buffett, who did a straightforward, hard but technically well-defined calculation. Namely, he calculated the Coulomb interaction contribution to the specific heat capacity. We have a linear spectrum in the density of states due to the linear electron dispersion, and this gives us, for anybody who is familiar with D-wave superconductors, the very same result, namely that the heat capacity is quadratic in temperature. We don't have a constant density of states. Density of states is linear, therefore we get another power. Good. He calculated the next correction, and the interesting result is that the sign is negative. And at low temperatures, there's a logarithmic term in addition to the t squared. At low temperatures, this logarithm will diverge and will dominate, so the heat capacity will be negative. And the entire conclusion from this result is that one has to be careful when one does this calculation. And the correction is not always small. It actually, at low temperatures, turns out to be large. And when in the calculation, therefore, one has to pay a little bit more attention on how one sums up the individual terms. Good. To do this, we want to compare briefly the situation of the Coulomb interaction with the ordinary electron gas. We want to compare what are the natural dimensionless units in the system And what is the importance of Coulomb direction? The result will be Coulomb direction in Dirac fermions or in graphene will be less important than in the usual Coulomb problem. But they will therefore be easily manageable. They will become manageable in a sense. If we have a p squared over 2m dispersion relation and the Coulomb directions in the usual electron gas problem, then the natural way to write this in dimensionless units is to introduce the mean electron distance, which is how the electron density enters the game. If I do this, and I just introduce dimensionless length scales where I divide the distances by the mean electron distance, then I get an overall prefactor. This is just a typical kinetic energy of an electron at the mean distance. And this is a dimensionless gradient operator, and this is dimensionless one over distance, and then I will get a dimensionless coupling constant, which I define this way. The usual way is to introduce some funny RS, but I've never understood whether large or small RS is strong or weak correlated. And there's a generation who knows it, and I'm not part of that. But we can understand that nevertheless. All we need to see is we just go to our dimensionless units. We have an overall prefactor of dimension energy, which we have to compensate. Here we have our charge, dielectric constant. At the end of the day, this is nothing else but the mean distance and the Bohr radius
You
ratio.
should switch off the lights.
Oh, yes. Thank you. So, and then we know what the implications are. When the density is high, the mean distance between carriers is small, and then we have the weak Coulomb direction limit. And that's because this goes like 1 over r and this goes like 1 over r squared. Right? And that's why the low density limit. And then we know what to do. We have free electrons and plasmons. We can treat the problem with the random phase approximation and so forth. Or we can go to the different limit where we have a large distance between typical carriers, and then of course our coupling constant becomes large, and this term dominates, and we should get Wigner crystallization and so forth. And this is the usual dimensionless analysis, how you fight between these two guys. Right? Good. And it is in particular that with density we can tune the strength of the interaction that causes all the well-known complications in this problem. If we have instead a linear here and a 1 over r, so 1 over r, 1 over r here, then these terms are actually of the same relative strength as far as density dependence is concerned for all densities. Right? We can repeat the same exercise. We divide this by the mean distance, we get a typical kinetic energy. On the distance, we get a coupling constant. The coupling constant is, in fact, as expected. It is the fine structure constant, E squared over h bar, but not C, but V. And so the dimensionless constant is just the corresponding fine structure constant of this problem, where all what has been done is that the speed of light has been replaced by the electron velocity, and of course we have the dielectric constant that I mentioned earlier. Given that the velocity here is significantly smaller, we have coupling constants that are significantly larger than 1 over 137. And in fact, if you plug in all the numbers and take the velocity of graphene, you find that it's 2.2 divided by whatever value for the Coulomb interaction you wish to choose. In vacuum, it should therefore be 2.2, period. And therefore we have an independent of the density. We cannot tune the strength of Coulomb interaction with the density. Yet we can tune it, for example, by sprinkling water on our sample, which experimentalists may not like, but this is how you could raise the dielectric constant significantly, right? Good. Now, the method by which we wish to study those terms I mentioned, there are logarithmic divergences here, will be just borrowed from what we've learned in treating quantum phase transitions in systems where we also have scale invariance as a natural ingredient of a description here at a critical point, and in this system also is scale invariant. Let's look at the kinetic energy. This is our spectrum, and now I'm zooming in and I'm actually getting the same spectrum. That's what I mean by scale invariant of that problem, right? If I were to have a parabolic spectrum, I would get the same, but in case of a parabolic spectrum, never mind now bilayer graphene, but the usual one, this is really only scale invariant if the system is empty. And that's not exact, this is also a critical point in that sense and has been discussed in this language, but it's a bit more trivial than what we are encountering here, because here we have occupied and unoccupied states that therefore make scattering possible. and cause to give rise to interesting Coulomb interaction. In fact, so what we are doing is we are rescaling momenta by some scale factor b, and then as a consequence, this problem, the energy will just scale the same way. Wow, it's linear, right? Good. In that sense, at zero chemical potential, zero magnetic field, zero temperature, and so forth, we can call this a quantum critical point. It behaves critical because it has perfect scaling variance. Right? But of course, once we introduce the finite chemical potential by a gate voltage, once we switch on temperature or magnetic fields, you will be pushed away from this critical point. And really what you want to know is how this happens, right? And you will just use crossover arguments in order to study the role of finite chemical potentials, temperatures, electron densities, and so forth on this problem. To see this, well, if I have a chemical potential that sits there, now I'm zooming in, it's obviously not scaling variant. That's what I meant by this, right? But the actual chemical potential rises, of course, if I rescale my variable. That's elementary of what I have in mind here. And so therefore, if I were to, for example, look at this problem, and I'm looking at it at very high energies, where this is a small chemical potential, it may initially appear to me as if it was a zero chemical potential. But once I'm looking at this at low temperatures or at extended scaling, then I will see that there's a large family surface and it looks like a two-dimensional family liquid. And therefore there will have to be a crossover from behavior that is like a Dirac to a family liquid behavior. And this is what we want to study, for example, right? And how this happens in detail. Now, this was all ignoring the Coulomb interaction, right? If I include Coulomb interaction, then, of course, once I zoom in, I also need to worry about the fact that states will sit here, Coulomb interact with states will sit there. And once I just eliminate them, for example, in a renormalization group sense, then I will have to worry about how the effective Coulomb interaction between those leftover states down here is being affected by shrinking and focusing on lower and lower energies. Good. So how would we do that? Well, usually what you do is you have some spectrum, and you want to look at the low energy properties of the spectrum, and you have some high energy states, and you say, well, I'm subdividing the system in low and high energy states, and there will be some coupling between them because they interact in some way. I can then effectively look at a low energy Hamiltonian and perform, well, just perturbation theory in the sense that I get effective decoupling between high and low energy states appropriately, right? And if I do this, then I get a new Hamiltonian that is, for example, in this case, depends only on a new coupling constant. And this is what we wish to study. And I will go through this in some detail because then we set the stage for how we want to treat hydrodynamics in the problem, how we want to study the DC conductivity, how we want to investigate, for example, the turbulence of electrons in graphene, and so forth. Those are all the issues that we want to address. But first of all, we want to go step by step and study what is this crossover and scaling behavior in these systems. If you do that and you want to look at the physical observable, that may depend, say, on a coupling constant, on temperature, on chemical potential, on magnetic field, then, and if the scaling logic applies, then what you will find is that there will always be a scaling, some function that needs to be determined that depends on the scaling parameter, and we will get to that, and of the same function at rescaled coupling constant, temperatures, chemical potential, and magnetic fields. We just saw how, for example, trivially chemical potential would rescale, right? Which would get larger. Yeah? So, for example, if the coupling constant under rescaling would grow, this would be a harder and harder problem to solve, and then we would have to resort to some complicated, strong coupling investigations in the problem. Here we are lucky. The coupling constant actually gets weaker, but it only does so logarithmically, and this allows us to actually solve the problem to leading order. And what we're doing is nothing else but, of course, parameters and so forth, renormalization group for that problem. Good. Now let's go, and here once again, I have 2D electron system and 3D electromagnetic field. That's what I mentioned earlier. And if you were to write on an action, so what I mean by this simply is the summation over momenta and integration over Matsubara frequencies. We need to keep this in mind in the following. So we have our Dirac spinor, we have our non-interacting Dirac problem, and we have a Coulomb interaction between densities. And now that's important here, since we are integrating over the transverse component of the Coulomb, of the photon momentum, if you want. So the Fourier transform, the 2D Fourier transform of the 1 over r interaction is not 1 over q squared. That is the 3D Fourier transform is 1 over mod q. Right? So the Coulomb interaction goes, the momentum stays like 1 over mod q. 1 over q squared would be the Fourier transform of log, right? Which is the actual 2D interaction of charges confined to so this is the problem we wish to study. Here is our coupling term, and this is our kinetic energy.
I'm sorry, I'm confused. You just said that the electrodynamics is not 2D electrodynamics?
The electric field can penetrate in three-dimensional space. That's all I said. That means the Coulomb interaction is 1 over r.
Yes.
That's all. That's actually what it comes down to.
All right.
And
then you're doing it.
And then you can effectively forget about the origin of the 1 over r interaction. Can from now on pretend you're living in 2 dimensions. But the origin, why you have mod q, which is non-analytic, right, is that you have a third dimension to integrate over in the typical momentum of the electrostatic potential in the qz direction. Right? So this becomes, in a way, a non-local theory, which has implications whether the theory is renormalizable. That's why it's a subtle issue that needs to be paid attention to. But at the end of the day, at this point, we can just pretend that's some given model. Right? Yeah. So let's once again ignore directions, and the procedure is very well defined. What you do is you just subdivide the system into low energies and some high energies, and therefore the momentum goes over the low energies, and the high energies have some scaling variable that is just defined by a little shell that I have here high energies. And if I do that, and then you would say, okay, as before, I'm rescaling my momentum, and let's assume I can always do that. I rescale my Graphene variables by some number with a coefficient that is given by the same scaling factor. And if I collect all of this, then I get the following coefficient here. I get here, I have a three-dimensional integration, more precisely a two-dimensional integration in the Matsubara sum. And I have one momentum k here that gives me number 4. And then I have two fermion fields that gives me 2 times the exponent. So this will be scale invariant, of course, if I choose rho equals 2, right? Then this will be 1, and I get the same action that I had for the low energy. That's what you do in parametrization. If you do that now and look for the interaction of electrons at low energies, not between low and high energies. So you use this result, you insert it in the Coulomb interaction, what you get is 1, 2, 3, 4 fermions, so you get 4 times rho, 4 times 2 is 8. You have 3 integrations because there's a conservation of momentum and energy, gives me 6 momentum and 3 from frequency, and then I have the 1 over q here. That's important. That gives me a +1. This is because I have Coulomb interaction. With the 2 here, 2 plus 8, and this is 9, minus 9 is 0. So in that sense, the Coulomb interaction is marginal, and that's what we said already earlier. We knew that already from our comparison of Coulomb interaction and kinetic energy, right? At all scales, it's the same one, right? So this would be the fancy way to write this at the flow equation at this trivial level, still that, say, the coupling constant wouldn't even change because this coefficient here is 0. But of course, what we have ignored is the Coulomb interaction between low states and high energy states. And once we do that, and the easiest to do that is by just having, looking at the leading diagram, which is the Hartree diagram, where you just have one state that is in here and that couples to a state that's out here, and is being kicked back. You have an integral to do, and you find that the integral here gives you a result. It's a simple, straightforward integral to take, and the scaling factor, the logarithm of this, gives me here a term that looks like a velocity and a coefficient, which is e squared over h bar epsilon b, which is our fine structure constant in a quarter. So that's, from there we learn that all what happens at that level is that the velocity of the system is being renormalized at a certain step of the renormalization group here to the velocity being increased by alpha quarters and L. Good. We can also look at other interactions. They happen to be 0 at other diagrams that occur, and the reason for this is charge inversion. So we can go through this exercise And now look at the same behavior here for the Coulomb interacting problem. Well, we cannot always assume that this will be power loss when we go from new fermions to old fermions, but some function that we will have to find out. I insert my self-energy here, and I ask, how do I need to choose this function to get scale invariant? And the answer is very simple. I just take this combination here. So this is just my self-energy correction. I have, again, two fermions here. I have a Matsubara sum. I have momentum integrations to perform. And the same exercise goes like this. And if you see, at the end of the day, you can collect an effective charge that's just given by all those functions that you choose, design, so that the action will be scale invariant. That it looks exactly like the action you started off with. And if you just do that, you find that the charge is the charge and something that is smaller than 1. And this you can, of course, formulate in a renormalization group language. Again, that the coupling constant floats, and it flows to a smaller value, and that's determined by the square of the coupling constant. That's what we call marginally irrelevant. It behaves just like statistical field theory in 4 dimensions, where we don't get new critical exponents yet, but where we pile up a bunch of logarithms in the calculation. Graphene behaves exactly the same. You can continue this to higher order, which is a detailed, long, and tedious calculation. We find that indeed this can be continued on to high order, so therefore we have some understanding that indeed this theory is renormalizable, which is, as I mentioned earlier, is not quite trivial. This was so far all academic, up until just a few months ago, simply because there were no experiments that would see this velocity renormalization in the system. And maybe I can conclude this talk today in pointing out that there's a very nice work from, I think, this February, where the Schubikos-de Haas oscillations were measured as function of carrier density on very clean single-layer graphene that was suspended, so it wasn't affected by substrate doping, nor was it affected by impurities. And at least compared to the other, to the usual impurity problems that you have when you put systems on the surface, and you find that this velocity renormalization, as deduced from the what they call cyclotron mass of the system, indeed can be understood very well in terms of the logarithmic enhancement of the that we just saw and that was predicted from theory. Basically, the way you have to look at this, it's a Dirac cone is actually not a Dirac cone, but it gets steeper and steeper and steeper and steeper as you go in, because the velocity actually diverges. Maybe one last comment: if you ask the question, well, if the velocity diverges, at some point it will be larger than the speed of light, that will violate the principle of special relativity. Of course, our theory here was done for a non-relativistic system because the Coulomb interaction was treated non-relativistically, right? And we have a clearly preferred reference frame in the system, which is one of our Coulomb interactions. If you do choose to include the transverse component of the electromagnetic field in the same calculation, then you find that this growth of the velocity stops. And it stops exactly at the speed of light. So light is in order. If you were to look at at very, very, very low energies in a perfectly clean graphene system, exponentially low temperatures, then you will see that the velocity stops growing logarithmically and it will reach a fixed point, and at that fixed point the velocity will reach the speed of light, and then you have a truly relativistic graphene, right? And not just a pseudo-relativistic in that sense, graphene. So maybe I just stop at this point. Is that, did you say 5 minutes ago?
You have 10 seconds left.
Yeah. Thank you very much.
Thank you for your impeccable time. Okay, it's open for questions. Yes.
I have 2 questions actually. First, can you say a few words about why you can neglect screening? Again, or why you did not take a screen potential?
Screen balance.
I don't know, the charges.
Well, if you write down Hamiltonian, it has to be the result of the calculation and not the assumption of the calculation that gets screened. Right?
Yeah.
The screening in Hamiltonian you should only include if you didn't include the perpetrators of the screening, right? So in recuperates we write down a local Coulomb interaction because there are lots of electronic states that play a huge role for those materials by screening the Coulomb interaction. But we don't bother including them in the description of the low energy physics, therefore we need to worry about them when we write down the model. And when we then get a result that there's phase separation, we need to remember that there actually is Coulomb interaction at long range and that we should reconsider what we've just done because the Coulomb interaction would, well, change very much how the phase separation takes place. But if you just write down the model, screening has to be the result. What can be a source of screening are, for example, metallic gates. If they were there, I would have to include in my dielectric constant not just a constant that can just change the value, but maybe a frequency and momentum dependent constant. The calculation can be performed as done here, but in some cases it will truly spoil the result because it will just give rise to, say, typical length scale changes. But there will be screening effects, but they must be a result of the calculation. Second question.
Okay, and it seems that the result is more general than graphene. You can say something about 3D topological insulators. I don't know, what is the Dirac cone on a topological insulator robust against interactions?
Well, here we have ignored a number of interactions that are important for topological insulators, such as spin-orbit interactions. This result is indeed applicable to all Dirac systems that interact via one of our Coulomb interactions. And I should point out, it was the velocity renormalization was first pointed out in a paper by Paco Guinea. What we did was to discuss implications of that velocity renormalization, but I can't start a talk about going to basics.
So the answer is that actually for a topological insulator, they should be the same. For surface
Well, if you can ignore other directions. I mean, here, let's compare sort of other interactions with this one. If you were to add phonons, which clearly are relevant, existent in graphene as well, right? They are less relevant than this interaction is, so at sufficiently low interaction, you can also ignore them. The answer is indeed, it should be the same if you have Coulomb interaction as the dominant interaction source. If you take short-range Coulomb interaction from some other source, maybe after you integrate out phonons, also they will be more irrelevant. This is the most relevant interaction that I think one can come up with. That is an electron-electron interaction.
If you do include spin-orbit interaction, that does open a tiny gap in graphene.
Yes.
How that will renormalize the...
Well, the logarithmic flow will stop at that scale. Yeah.
And you're not reaching the...
Well, no, the experiments don't do either. Yeah.
Well, spin-orbit is there.
Right, and it's not very large.
It's very small,
Right, and that... See, this is just like when there's an experimentalist who tells you that there's a scaling of the temperature dependent, say, the Raman spectrum or something. And then you should always keep in mind that there might be excitations at much lower energies that he's just ignored, right? So that can always happen. Yeah.
I have a comment followed by a question,
Yes.
if I may.
Of course.
As you mentioned, so there are different ways of producing graphene. So the isolation as the Nobel Prize group, but also the growth on a silicon carbide, for example, so epitaxially you grow a layer. And when you do that, you can do that either silicon carbide has a C phase and a carbon phase and a silicon phase. And as a matter of fact, the material that you get when you grow graphene on one phase or on the other is different,
Yes.
apparently
Yeah.
from
Yeah.
different experimental
Yeah.
evidences. And in fact, we've measured on the carbon phase, but we've measured on silicon phase as well. And the difference is really striking. As on the silicon phase, we observe the nice data that you have shown from the Ultra-Boost group, okay, with velocity renormalization and even more fine effects occurring there in the band structure. But on the carbon phase, in fact, we do not observe these deviations from the linear dispersion. We really observe very linear bands very far away
At low energies
yes.
or high energies?
Sorry?
At very far down to low energies or very far up to high energies? I just didn't. You see linear bands very far, I just didn't know which way far.
Well, below the Fermi level, I mean, we're
Okay.
doing further mission.
Okay.
And we've done that as well as thin films than thick films, you know. So we want you guys to help us understand this discrepancy. We believe it's really related to the system itself. On the carbon phase, you know, we have a new rotational ordering occurring there. And yeah, it might be related really to that. So do you have a...
Well, of course I'm not going to find it right now. So first of all, if the dielectric constant of these two systems is actually, I believe, very similar, right? It's just a different surface reconstruction, right?
Yeah.
So what you typically find is when you put things on the surface, it's harder to find those velocity renormalizations, simply because you have the dielectric constant of the substrates, silicon carbide, I think 5 point something or so, or 6. So then you get an effective dielectric constant of 1 plus 6 half is close to 3.5. So therefore your coupling constant is just lower. The effect therefore will only become important at much lower energies, and it's much harder to see. That does not explain what you point out, namely that there's different behavior in different surfaces. I simply, very brief answer to your question, I have no clue. But one thing that one has to keep in mind is when you put things on the surface is whether the two sublattices in the carbon unit itself are actually still identical. And in some cases they are not, and just STM sees that they are not behaving the same. That would then give rise to, of course, an opening of a gap in the Dirac spectrum. And it can spoil some of the results, and maybe you could interpret them in various ways. So I would have to really look at the data to say anything more intelligent than that. Yeah.
Because indeed we have seen that.
Yep.
Yeah, I think I'd just make a very quick comment about that. I know that also was done in Berkeley.
Yes, they did. They did see the logarithmic change. At least they could fit the data in a consistent way with that.
Maybe you're going to raise this point about the inelastic X-ray scattering that was done by Peter Abamonte at Graphene.
Yeah. Well, that's it. So let me comment on. Shall I comment on that, or should I not? I don't need to.
I have a different question.
Oh, you have a different question. Okay, let's go with a different question.
And the picture of Patrick Guinea and co-workers, there's a divergence if you go to the Dirac point.
Yeah. Just this is an experimental paper. I think the primary credit goes to the. No, it is great.
Okay. He used to ask also.
Yes.
So my question is, so what sets the density scale? So
Gate voltage.
no, my question is, so there is a divergence of the velocity, right? And
Yes.
this starts at the typical density.
Yes.
So what is this typical density if you look at calculation?
Yes.
So
It's exactly what we will be discussing in the next lecture. If you are still here, otherwise I can answer right away. Yeah.
Can I ask?
Yes.
Yeah. In your self-energy calculations, you only consider the lowest order term, which is the Hartree term.
And the next order, but that was very briefly mentioned only.
Yeah. So my question is like, so you get a renormalization which is energy independent.
Yes.
But if I look at the R test, there is a key, so the renormalization changes.
I think it's phone.
And you think that's phonon? But there are other calculations which say, so
I know.
if you include higher order term, can you get that or not?
Well, let's not talk about ARPAs for the time being, but this is a surprising result on its own right for the following reason. Here you see at least to very low energies, because of very low densities, and therefore typically at large distances and low energies, you see this logarithmic divergence. It's a suspended graphene, the coupling constant is 2.2. You can ask yourself, what does Coulomb direction actually do in that system? Because what we have seen is that you flow to smaller and smaller coupling. if you switch on a computer, you find that at sufficiently large coupling, the system will, just Coulomb interaction, which drives the system into an insulating state, where you open up a gap. It's a spontaneous symmetry breaking the system. And it says it should happen at 1.8 of the coupling constant. So therefore, we should actually be in an insulating phase in that system. So maybe there's some screening that puts us here close to the site, but there's an interesting problem that we actually see this behavior. So therefore, the calculation I've done is the coupling constant gets smaller and smaller. We are attracted basically by this fixed point. And so far, there's no experimental indication for this phase transition. There's very interesting physics related to this phase transition, which I'm not going to get into right now. Now, kinks. I think what's been seen there are phonons. You can, at finite density, get kinks also from plasmon excitations in the system, and that is another option that's perfectly well there. And to distinguish the two, you just change the density and check whether the kink moves or doesn't.
But my question was even simpler. So if you include your higher order terms, you'll get some
You
energy
mean
dependence. No, yeah. In
Yeah,
that case.
here we also included those same higher order terms that you would
And
call
what kind of
plasmon
energy
density.
dependence
There's
is
no
the same?
kink. So the answer is there's no kink at the
You don't
symmetry
see it.
point.
Okay.
Yeah.
Okay.
Yeah.
Yeah, going back to Girsh's question, so what is the scaling of the gap induced, let's say, for spin orbit interaction with lambda? So let's say you have spin orbit and that opens a gap. How the gap scales with the spin
I
orbit?
believe it is
Square root of lambda c or?
It is lambdas. No, it's a high order effect. It
It's
is.
relativistic effect.
Yeah, but even if it's spin orbit interaction, it's not linear.
Yeah.
But
Is it
it's
square root or linear?
So in other words, it can be big. I mean, can it be? I mean, that gap can be big, or it will be always very small.
No, I don't think it can be big. I think it's very small.
It's always relevant.
Yeah.
That's a question. You always go to the gap. Right?
Yeah. No, it's always relevant. Yeah, but I mean,
I don't know if that's.
yeah, but it's always there. But
Yeah,
I
my
think
question is if it goes like square root of lambda or lambda.
for all relevant experiments thus far, it has not played any role whatsoever.
Which is surprising.
In the back.
Is this number 1.08 really known that precisely?
This Monte Carlo calculations. They did finite size scaling analysis, and well, I think they gave an error bar that's somewhere here on the
So
statistic.
this is not 1 over n. So this is
Oh no. Well, if we do 1 over n, oh yeah. Here's the phase diagram. N fermions and coupling constant. In 1 over n, you never even get the transition. You only get it when you have short range interactions, but not this long range interactions. So you never get this 1 over n. This is a number obtained from numerics. There's another interesting result. The numerics tell us that this is a critical point, exponents. All existing mean field calculations say completely different. So there's a very interesting open problem as far as this metal insulator transition is concerned. Because there's some strong coupling physics that's very, very interesting. And it's in the regime where we have suspended graphene. So it should be something that's experimentally accessible.
The insulating phase is something like this.
Oh, the two sublattices of graphene are just different. You just accumulate some more charge in one and the other one. There's no real Wigner crystal on the Dirac lattice because the Coulomb direction is never strong enough. But it is a charge ordered state.
You told us about Buffett's calculation, which was a straight
Yes.
perturbative one. Now you've gone beyond this. What's the answer? Further specifically, did I miss that?
No.
Ah.
If you do the same, really what you do is ignore this here for the time being. This is the heat capacity result of free fermions. Now I'm replacing the velocity by velocity renormalization, and the scale, the natural scale, if I raise temperature at the critical point, is temperature. Just cross over recently. So I get this correction. If I do a Taylor series expansion in small alpha, I get 1 minus alpha and so forth, exactly what you get. But the leading term at small temperatures is just drop the 1 in this one. This is the right result, right? I mean, he was aware of that. He's a smart man.
I know.
That's what big eddy, but but this is how you would get this, and you can also see this here. We were, if you go down in temperature at the neutrality point where you have Fermi level just at the zero point, then you get this T squared over log squared T behavior down to lowest temperatures. And of course, once you go away, you get linear in temperature behavior because you got a Fermi liquid. But with a coefficient that depends on density exactly, so you match at these points the same down, right? So that's where you have a Fermi liquid, zero liquid crossover in the system. Yeah. Thanks for that.
Any other questions? Okay, if not, let's